Hi, I'm Teacher Thomas. Welcome to A-Level Maths. This is 9231 Further Probability and Statistics, Topic 3, Chi-Squared Tests. This is from paper November 2019-21, question 11b. The number of puncture repairs carried out each week by a small repair shop is recorded over a period of 40 weeks. The results are shown in the following table. Requirement 1. Calculate the mean and variance for the number of repairs in a week and comment on the possible suitability of a Poisson distribution to model the data. We're going to calculate an estimate of the mean, and we'll calculate an estimate of the standard deviation. In order to do that, I need some calculations from my table up above. The total number of weeks, adding across the second row, is 40. And I need to have the multiple of the number of repairs in a week times the number of weeks available as well in two different formats. In the first format, I'm simply taking number of repairs and multiplying by the number of weeks as I've written out. That's going to sum to 68. And in the second format, I need to square the number of repairs and then multiply. And that calculation is going to produce 178. And now for the estimated parameters for the estimated mean, I'm going to take 68 over 40. 40 is the total of the weeks, and the 68 is the multiple of the number of repairs times number of weeks. This simplifies to 17 over 10. And for the estimated, I have the notation for standard deviation. I want the notation for variance. There we go. I'm going to take my sum of x squared times frequency. That's the 178. Over number of weeks, 40. I will subtract the mean squared. The mean I've just calculated above, 17 over 10 squared. And this result is 39 over 25. Regarding the possible suitability of a Poisson distribution, the implication here is that upon evaluating or calculating the estimated parameters, we'll see something that gives us insight into suitability. So let's change these to decimal, or show the equivalent decimal, 1.7 and 1.56. And I observe that these two parameters are similar, and based on the similarity, I state that a Poisson distribution might be suitable. Going on to requirement 2. Records over a longer period of time indicate that the mean number of repairs in a week is 1.6. The following table shows some of the expected frequencies correct to 3 decimal places for a period of 40 weeks using a Poisson distribution with mean 1.6. Requirement 2. Show that alpha is 0.706 and find the value of the constant b. So I'll change that from alpha to a since the second variable is b. The proof of A, I want to use the Poisson for the value of 5. So I have e to the power of the negative mean, negative 1.6, multiplying by the mean, 1.6, to the power of the number of repairs in a week I'm looking at, 5, over that same number, 5 factorial. We want to multiply this value by the 40 weeks involved in the analysis. That result is 0.706. So that matches to the value they've given me to prove. For B, I'm not doing the same process changing the value from 5 to 6. I want to calculate the residual based on what goes into the final expectation is 40 minus, and what we're subtracting is every other measurement. That A we've just solved for, so we can sum those measurements. 40 minus that sum gives us what we want for B, and that value is 0.242. If you were to calculate the Poisson using a value of 6, you'd get less than 0.242. That B needs to incorporate 6 or 7 or 8 or 100,000 or 20 million. As unlikely as those numbers are, they're non-zero probabilities. So the correct way to calculate the B, again, here is as a residual of 40 minus everything else. And requirement 3, carry out a goodness of fit test of a Poisson distribution with mean 1.6 using a 10% significance level. The values we need for this analysis are on the prior slide, so I'll change to red, and marking up this screen in red relates to requirement 3. First, I'm going to observe my expected frequencies have some values that are less than 5. Those are, I want to change to red. Number of repairs in a week of 4, and 5, and 6. Those are all less than 5. So I'm going to roll those into the column that we have currently written as 3 and change that to 3 greater than or equal to 3. And when I sum the expected frequencies, I get the value of 8.666. So notice now we have 4 categories, 0, 1, 2, and greater than or equal to 3. These values are my expectations. I also want my observations. Let's go one screen back and get those. Here we're also going to combine into one category the greater than or equal to 3, the weeks relating to 3 on. So I see 6, 3, 1, and 0. Those are going to sum to 10 for the category greater than or equal to 3. And then the category 0, 1, and 2, I have 6, 15, and 9. Next I want my chi-squared statistic. This is going to be the sum of all expected minus observed quantity squared over expected. I'll talk through the first calculation and then write the others out. In the first calculation, looking at the number of repairs of 0, expectation is 8.076, observed is 6. So I subtract 8.076 minus 6, I square that value, and I divide by 8.076, and I get 0.534. And working across, the next value is 0.334, then 0.173, finally 0.205. This last value is coming from the calculation based on 4 combined categories. That's the 3, the 4, the 5, and the greater than or equal to 6. A combined expectation, a combined observation, using those combined values for the calculation. When I sum, I get my chi-squared statistic 1.247. Carry that over. From here, I want to identify degrees of freedom. I have, looking back, after combining, I have 4 categories, 0, 1, 2, and greater than or equal to 3. Standard -1, minus any estimated parameters. Here 0 In part 1, we did estimate the mean, but we're using the given mean of 1.6 in this analysis, not an estimate, so we don't have any estimated parameters. Result is 3. So I will look up the critical value for chi-squared with degrees of freedom of 3. 10% significance per requirements, I'll use 0.9. The result is 6.251. Now I'm going to compare, but I realize I need to complete an earlier step, which is the identification of the null and alternative hypotheses. And here they are. The null hypothesis, Poisson distribution with a mean of 1.6 is a good fit. Alternative hypothesis, Poisson distribution with a mean of 1.6 is not a good fit. From there, I calculate my chi-squared. Then I have my critical value lookup. Now, with those values, I compare. 1.247 is less than 6.251. I conclude, do not reject the null hypothesis. And I describe what this means. Poisson distribution with a mean of 1.6 is a good fit. This completes the requirements for 11b.